All right. So today, again, heterogeneous graphs and knowledge graph embeddings. So we've talked about graph neural networks, had a number of different sessions about that, and other things about graphs. And so we are going to extend some of those concepts for heterogeneous graphs, and in particular, talk a little bit about knowledge graphs and some work people have done in creating embeddings and using embeddings for knowledge graph completion. So there's a couple different models that we'll discuss: the TransE, TransR, dismal, and complex, and you'll see what those funny names actually mean in just a little bit. So here's the deal. So far, most of the lectures have been focused just on like undirected simple graphs with one edge type. And sometimes there's been comments that, hey, this can easily be extended to directed graphs, or this could be extended to graphs with more, but we haven't really talked about it. And so now we're gonna go into some very explicit discussion about what do you do when you have these heterogeneous graphs with potentially multiple node types and also multiple edge types. And as I said, so we'll talk about these relational graph convolutional networks as an extension to regular GCNs that we've already talked about, and then we'll get into knowledge graphs. All right, so the first thing is RGCN and heterogeneous graphs. So a normal simple graph, you would just say the graph is defined, G is defined by two things, just your vertices and your edges. And every edge, connects a pair of vertices. But now we also need these extra things, these R and this T. We need four things because we need to say what type of node is each node, and we need to say what type of relation is each edge. So it goes from a pair, a two-tuple, to now a four-tuple. And in the slides, there's many different examples of heterogeneous graphs. So you could have a biomedical knowledge graph, and you could have things like, here's a diagnosis, here's a symptom, here's a drug, here's a protein. There's an example here on the right, event graphs. I think we have a couple more slides. No, but so we'll see. There's no shortage of things, obviously, that you can model pretty much anything as a graph. And so just to recap, so how do we run a GCN on a directed graph that only has one node type and one edge type? So if you recall, when we talked about GNNs, basically what we said is that we're going to use the neighbors. And in this case, now we're talking about a directed graph. So this is only the inward coming edges, okay? And so for node A, it has inward coming edges from B, C, and D. And so we're going to take information from B, C, and D, from that local neighborhood. But we know that if there's a second layer, that each of those nodes, so in particular B and C, could be taking in information from their neighbors. And in this way, if you have, say, a 5-layer graph neural network, then you're really pulling in information from your 5-hop neighborhood. And you don't necessarily want a super deep GNN like you often do in other areas like NLP and computer vision, because if you get super deep, then you're taking information from the whole graph, and you have this phenomenon we talked about where the embeddings tend to actually look fairly similar between all the different nodes, just because they're all taking information in from the entire graph. All right, so you typically see less deep networks. And so formally, what is this information that we're taking in? So we say that we get a message from each of these nodes, and then we aggregate them in some way. A very simple thing we could do is we just take the embeddings from those other nodes. That's the message. Simple thing we could do is we could just average them or sum the messages, coming from our immediate neighbors. And typically, in order to increase the expressive power, we're going to add some sort of nonlinearity. And again, this looks just like non-graph neural networks that we've talked about. So you have sigma, ReLU, whatever. You can use all the exact same things in our tool belt that we use for graph neural networks. And all the other things that we talked about still apply, skip connections, whatever, but those aren't particularly relevant to how do we now deal with heterogeneous graphs. Okay, so here, graph convolutional networks were the first GNN we talked about. They're simple, so they aren't doing any fancy message creation. They aren't doing any fancy aggregation. What they're doing for the message is they're basically taking a well, you see the equation on the top is you average all of the messages coming in, then you multiply it by your weight matrix. So just like any neural network, you kind of have this weight matrix, right? But if you sort of rearrange things, then you can think of it as you multiply by the weight matrix before you sum them up, just so that like you get this paradigm of the message in the red box and the aggregation in the orange box. So in that case, basically, you're saying the message is you multiply your weight matrix by just the embedding of all your neighbors. In this case, they're already scaled, so you sum them up. Hey, Yan, would you mind just muting the other participants? I think there's just a little, yeah, there's a little background noise. Nothing intentional, just a little background noise. And so in this case, because they're already scaled, then we just sum them up, no biggie, okay? And then after we apply some nonlinearity, some activation function, that is our new embedding. And this is exactly what we're gonna use. This H is the same thing we're gonna use to pass on if we're passing on into another layer, okay? So this is the simplest form of GNN, where you just start with the natural features for each node. That's your original embedding, your H sub 0. And then as you go through different layers, these embeddings get modified and combined, and ultimately you get some set of information that's an aggregation of everything in your neighborhood. All right, so that's classic GCN, no heterogeneous network. So now the question is, what do we do when we have multiple relationship types? So here you see the edges are different colors to correspond to, there's different types of relations. R1 is blue and R2 is red. Okay, so a simple thing we can do is we can use different neural network weights for each of the relation types. If we think about it, there's like various ways you can try and like optimize this or think about this mathematically, but however you do it, whether you do it in some super efficient manner or not, you basically simply say that I'm going to sort of, consider all the R1s, all the blue edges differently than I can consider all the red ones. And how I'm going to do it differently is that I'm going to have completely different weight matrices for each of them. So ultimately then, when we do our aggregation, we're aggregating over different relation types. And hypothetically, if we wanted, like if the weight matrices learn the right things, the different relation types could actually be correlated. They could have certain commonalities in the weight matrices. So let's say you had, I'm just making this up, you had relationships for like sibling, parent, child, or something like that, right? You might actually like for there to be strong correlations. You don't necessarily want all of those relations to be completely independent of each other. And that's possible. Now, obviously, what actually happens, when you train a neural network, you can't guarantee that's going to happen. But clearly, there is the ability for the weights to have correlation and not just to be completely independent. So here's a little bit more formality. I don't think that it's really necessary to go through this in too much detail. The main idea here is that you see this equation's in black, but in blue, we now have, instead of just the weight matrix for my node times the message coming in, I actually have a per different kind of edge, per different kind of relationship weight matrix. And then the rest of these equations are fairly straightforward in terms of, you're summing things up. And if you look closely, you'll see that you also have a special weight matrix for yourself. And that kind of makes sense. You could think of that as another relation type. Like, you technically only have R relations, but you could have an R plus first one, which is just self. And you can have a different weight matrix for how you aggregate data from yourself from the previous time step, so to speak. All right. So if you do this, a little bit of stuff about scalability. If there are L layers, you always had L weight matrices. The weight matrices are shared across all the nodes, but you have one per layer. The problem is if you have R relations and they each have these, then of course you're going to wind up with L times R total weight matrices. And the size of each of these matrices is roughly D squared, where D is the size of your embeddings, the number of hidden dimensions. So this can grow really fast. And there's a note here in red that overfitting can become a real issue. Okay, so there's two tricks that people use to regularize this and to kind of trim this down. I think both of these are pretty straightforward, interesting. So one is block diagonal matrices. So if your weight matrix, instead of just being fully dense and having non-zero values everywhere, if you define some block diagonal form and you say that only these entries near the diagonal are allowed to be non-zero, then obviously this sparsifies it and has many fewer non-zero. But there is kind of a problem that imagine that you had this sort of 2x2 structure, then basically you can see that like you know, stuff from like node 1 and node 2 can interact, but stuff from node 1 and node 3 can't interact because these entries are all zeros. So maybe if you think about it, if it's deeper over time, those could eventually sort of percolate, but I think it's a little bit tricky. So you have to kind of, I would imagine you would have to definitely play around with the hyperparameters a little bit in order to try and get enough information, but also try and cut down on your weights and your compute time. So another approach you can do is basis learning. So basically, what the basis refers to is that you have a set of building block matrices, and you simply say that my weight matrix for relationship 1 is going to be a linear combination of all these different bases. So if I pick, I don't know, 16 bases, then it's some constant times matrix 1 plus some small constant times matrix 2 plus some constant times matrix 3, all the way up through 16. And so if that's the case and your basis matrices are fixed, then basically all you're doing is you're just learning the 16 weights. It's not clear to me whether the bases are fixed or whether they're also trainable as part of, the gradient descent backpropagation. But even still, even if they are, the key thing is that those bases are shared amongst all the different weight matrices. And so it dramatically, you're now learning roughly the same number of parameters as a regular GCN. So even if you had 100 different relation types, you still basically have that set of bases and then just a few scalars that you're learning in terms of how you're going to combine them. So I thought that was pretty cool. All right, and so if we use this GCN, and we could also extend these very same concepts to the more complex GNNs, okay. What are some things that we might do in this model, and how does that look compared to in the simple graph, compared to the simple graph, right? So one thing we might do is like node classification. All right, pretty straightforward. So we train our GNN, and then basically once we have our embeddings, we can apply just like we do in non-graph machine learning, right? You have a final layer, you apply a softmax on that, and then basically if you have K classes, you have K nodes, and we can interpret the outputs of the K nodes after the softmax as the probability for each class. That's pretty much the way we do K-way classification everywhere else, right? No different. There's a couple slides here on link prediction, and link prediction is just a little bit trickier than in the simple graph case. And so this slide, I'm not going to read all the stuff on here, but basically, if you're familiar with stratified Um, 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 oh, now I'm totally blanking. If you're familiar with cross validation and the way that we do stratified cross validation, all they're saying is that you should do stratified cross validation. So when you're splitting up your nodes and edges into your training and validation sets or whatever, it's possible that a particular type of edge is rare. Not all the edges necessarily are equal in frequency, okay? And so just like we have a concern potentially with a certain column has, you know, few values of interest, we might want to stratify on that when we're doing our train validation sets. They're saying the same thing here. They're saying that, oh, maybe if this orange type of edge is very rare, we just want to make sure that we're stratifying and we're splitting. So what they recommend basically is that you split on each relation type separately, and then you merge them together into your training and validation sets. Okay, so there's a couple more slides here on how you actually do the link prediction. Not sure if there's anything really different here from the that much different from the simple graph case, but basically, you know, if we're looking at predicting whether or not there's an edge between E and A, then basically what we're going to do is we're going to score it for the different relationship types. And then basically you can see if you get, right, like a really high score, then that's predicting that there likely, you know, will be an edge between E and A. So I don't see this as being very different from the simple graph case, except that I guess if you have 3 different relation types and you're thinking it might be any one of those, then you score it separately for relation 1, relation 2, relation 3. And so there's, you can review the slides, but there's a little bit more detail here in terms of how do we get our negative samples. We're going to talk a little bit more about knowledge graphs and the fact that they tend to be very incomplete. But so one of the things that typically is done when you're training is that, of course, you're going to train it on the positive examples. The positive examples are the edges that you actually have. Typically, you also need counterexamples, and so you're going to have negative examples. And so what you can do is, they call this corrupting the tail. So basically, if you currently have edges that go from E to other nodes, and you say, okay, I only have one, I have a node from E to A, then I can just corrupt this by changing the A to some other node and saying it's probably a negative example. So one thing you need to do is you need to explicitly make sure that you don't accidentally pick an edge that really does exist. So you have to do that extra check. And other than that, I think it's just a probabilistic thing that most of the time, you know, just given the general sparsity of graphs, that if you're picking a random other edge that isn't part of your graph, then it's going to be a valid negative example. I think some of the papers even talked about, you know, potentially increasing the number of negative examples depending on the problem you're training on. You might need more negative examples than just like one-to-one. All right, and then the rest of this, I think, just follows the standard process in terms of binary cross entropy. Whenever we have a model that we want to predict, you know, binary outcomes, yes or no, whether or not there's an edge there. And so a couple more details here that you can go through on the slides. But essentially, the rest of this looks like what we've talked about with regular GCN and also just what we do every day in non-graph neural networks. So I'm going to sort of save more time for the knowledge graph stuff. So I'm kind of flipping through these slides quickly. So in summary, we can extend GCN to this relational GCN examples for node entity classification and link prediction. And this same type of extension you can also do for any other of the GNNs. And so like GraphSage is pretty generic in terms of it allows for a wide variety of message formation options and a wide variety of aggregation options. And so you can very easily turn GraphSage into R GraphSage. Okay, so that's the early intro, talking about if we want to extend our GNNs to heterogeneous graphs. Any questions, comments?
It is just, you know, it's getting all so complicated comparatively to usual graph network. So is there any example, working example of this, efficient working example?
Yeah, there are libraries, and maybe one of the things to do is to look for an example. So next session Ryan's gonna do, but the session after that is kind of open, and so maybe one of the things I'll do is I'll look to see if I can find a package that's doing RGCN or something similar, and then you know, show you guys training it on a small heterogeneous graph. Anything else? I see some comments in the chat. So again, I didn't look to see whether or not those basis matrices are learned or whether they whether they're just generated at the initialization and then static. But yes, you would definitely want full rank matrices as your bases, right? So so I think that's, you know, so even if they are learned, thanks Vance, then I think you still, I don't know, maybe you can just trust random. Maybe you can just trust random, but it'd be nice if you just checked and made sure that they're all full rank before you start training, so that you're not potentially handicapping your learning, right?
I doubt that they're random, because they should be far enough apart for discern for different types, for different relations.
Okay, thank you.
I guess I'm a little bit stuck on this part too, because I feel like all of the representations of all of the relationships should be able to be represented by the basis, but I don't understand how that looks like in this problem.
So let's say we have nodes. Thanks for the question. Let's say we have nodes that inherently, to begin with, it's like people, okay? And we have 50 things that we know about people. We know their history with our company. We know something about their geography. We know something about their age, their gender, whatever. So we have like 50 features. So before we've done any graph neural network, before we've done any training stuff, right? We can have a embedding for each person that's a vector of length 50. And in the simple graph case, what we said is we build these graph neural networks, and they collect information from their neighbors, and they aggregate it in certain ways, and over time, as you train them, they build node embeddings for each node, which not only start with the original information they have, but have now somehow managed to incorporate information from all of their neighbors. When they're doing this, they have a full 50 by 50 weight matrix for each layer that is used. Okay, in this case, if we now have, I don't know, 32 different relationship types, we can do the exact same process without any modification, but now we're going to have 32 50 by 50 weight matrices for each layer. And there's the possibility that we don't have enough training data, so that this whole thing then just overfits and it just sort of memorizes, you know, our training data, right? So the idea is that these 32 50 by 50 weight matrices, instead of having them each be completely independent and have their own arbitrary weights, if you said, I don't know what's a good size for basis, because like I said, this is new to me. But let's just say you even made it kind of big. You said, okay, there's 256 basis matrices. And of course, there will just randomly be some collinearity, some duplication, whatever. But if you can have any linear combination of those 256 matrices as your weight matrix, you could have a lot of variety of different values in your matrix if you are, just combining these 256 different weight matrices. And so then, but the idea is that if you extend this to like a knowledge graph that has like 30,000 relationship types, it's much better to have just a small basis like 256 than to have thousands of different relations and then exploding numbers of weight matrices. I don't know, is that pretty much the same thing I said before, or did I say any better? Did that help?
I think baby steps will get there. Thank you, though.
Okay, all right. And if anybody else can help, please as well. Okay, so then I think we'll move on to the knowledge graphs, and I'm pretty sure, generally speaking, in the slides there are links to papers, and so I don't remember, but I think there may be a link for the basis learning, since there seems to be a number of comments in the chat about that. All right, so now let's talk about a specific kind of heterogeneous graph. I've certainly seen gazillions of mentions of knowledge graphs, even though, again, I haven't actually had to do any work with them yet. So generally speaking, knowledge graphs are the form where your nodes are some type of entity, and you have the relationships between them, depending on your domain, and typically, you think of the edges as triples. So there are, in fact, specific databases that are like triple stores, right? So, so in this case, a node from entity 1 using relationship type whatever to entity 2. So here's some examples. Here's a bibliographic network. You could see the different types of entities you might have are papers, conferences, authors, and so you can have an edge that's of type, this paper has author so-and-so. Some of these can be one-to-one, some of these can be one-to-many, right? And even things like, okay, papers that cite other papers, that's actually from one entity of type paper to another entity of type paper. Here's a biology knowledge graph. So again, now you have things like drugs, diseases, proteins, and then relations are things like, causes associated with treats, things like that. And I don't know all of these examples. If anybody is more familiar, you're free to share here, but here's just a list of knowledge graphs that are currently in use that you may have heard of. Knowledge graph behind Google, behind Bing, Facebook graph, LinkedIn, stuff like that. So I don't know if anybody has any thoughts or comments about any of these mentioned here. I'll just say that they're really big. That's the one thing I know.
Google got to start with Freebase, which was an open source knowledge base of all music albums, and then it turned into movies, and then it turned into basically all knowledge. And so when it got big enough, Google just bought it and made it closed source.
They closed it, really?
Yeah, well, they left the old data, but then they tore down the system that was used to create it by the community and took it internally. So all the old data is out there and you can download it, but it's not live anymore. It's not keeping up with the times. So they just internally created their own format and incorporated it into Google Brain.
Thanks, Hobbs. Okay, and then some examples here. So if you ask for the latest films by the director of Titanic, then obviously first you need to be able to say who is the director of the movie Titanic, and that's probably pretty easy. But then what are all the other films that were directed by James Cameron? And if you have a knowledge graph, that's relatively easy to answer. But if you don't, then the number of possible places you need to look in order to find that information is pretty large. And so you can see why for a use case like this, having that graph would be very helpful. They mention knowledge graphs used in question answering and conversation agents. And I think this can get very complicated, but it just makes sense that basically, you know, if you're doing question answering, then you want to be able to take sort of, right, the question that's being asked, figure out the named entities in it, figure out the relations that are in it, and then basically translate that to, you know, do I have information? Potentially you can supplement this by doing a search on Wikipedia or doing a search on the internet, but clearly having like a knowledge graph of information would be very helpful for a use case like this. So mentioning some data sets, I'm not familiar with any of these. There's the old Freebase, the Wikidata, DBpedia. And so two characteristics that they highlight is that they're very big, they're massive, okay? Generally, you know, in the millions or more. And another thing that people know about these is that generally speaking, they're very highly incomplete. So one of the things that we're interested in is, can we predict plausible links that are missing? So the example he gives here is that Freebase, 80 million entities, 3 billion facts, 3 billion triples, 38,000 different relation types. But of these, you know, one of these is place of birth, and 93% of the people in this database don't actually have that relation type specified. And even nationality, which is more generic than just the exact city where you were born, it's still 78% of them don't exist. So these are an example of just how many missing links there are. And so if you were looking up in this database and you wanted to know, you know, where is this person born, odds are you wouldn't know that. And so you could potentially use completion in order to get an answer for that. So talking about this problem, so let's look at this graph over here. By the way, one thing I thought was kind of funny is they talk about these relationships as starting from the head node, going to the tail node. And so we're not doing generic link prediction. We're doing link prediction where you specify your head starting point and the relation type. And so all you really are trying to do is to predict the one or more nodes that are possible answers for the end of the triple. But I did think it's kind of funny because this concept of head and tail is kind of backwards in terms of, like, when I think of an arrow, the head of the arrow is over here. So anyway, I don't know if that confused anybody else, but I had to pause for a moment just because it was opposite from the way I thought it was going to be. So in this case, we may have this node. I'm trying to see. Oh, this node here is J.K. Rowling. I had a little trouble reading the label, right? And so we have these existing things that say influenced by genre, and then, you know, is there another genre that's missing? And can we predict whether or not science fiction is the missing genre for this person? That kind of a thing. I don't know if anybody, one of the questions that I had, I don't know if anybody has sort of a real world example of knowledge graph completion, because I was thinking about it a little bit, and it's sort of like, well, if you're doing like a Google search or whatever, maybe they use it or whatever, but it seems to me like you don't necessarily want to like guess as to like what the answer is. So like, you know, if you're guessing the nationality of a person, like that doesn't seem like a very good thing to just like be guessing based on completion. But
it would be based on other facts, so there'd be some confidence in it, and there's some like it's not 100% confident even on the existing links. So it's a way of inferring knowledge from other knowledge.
mm-hmm. Yeah, and it seems to me that like maybe if you're doing something with like drugs or whatever, you know, and if you're trying to if you're trying to say like, oh, well, maybe this is whatever the part of the pathway, or this gene or this protein or whatever, you know, participates in this, it's not like a Google search where you're just returning this answer. You then you go do some experiments to actually see whether or not like the thing that it predicted actually is true or not, or something like that.
Yeah, and it's almost always used among many other possibilities. So it's usually a ranked list of possibilities of things that you might be interested in, whatever you're working on. Just like the most probable most probable answer at the top of the ranked list.
Yep. Okay. So in the remainder of this session, what we're going to talk about is how we can solve these types of problems with shallow embeddings. So these embeddings are like word2vec type embeddings, okay, where you just have a separate independent vector associated with each node, and you use these embeddings in order to test out different relationships. Okay, so right now we're stepping away from graph neural networks. So once again, edges represented as a triple from head with relation R to the tail. And what we're going to do is we're going to have an embedding space of dimension D. And in this case, what you'll see is that not only are we going to have an embedding for each node, both the head and the tail nodes, but we also are going to require an embedding for each relation type, because we actually need every relation to work differently. So it requires, you know, its own data as well. And the idea is that we're going to have some measure of closeness, some function that gives us some sort of score or distance. Don't take distance too literally, because it's not always like a, you know, like a measure distance, but some kind of score. And so the idea is that you want to be able to score, hey, if I give you this head, this relationship, and this tail, do they score well? Like, yeah, that looks like a really good fit. Or no, this tail seems nowhere near that what you would expect for that head and that relationship. So that's how we're going to do it. So we do need to define, we need to figure out how to do the embedding, and we need to define the closeness. So the simplest thing you can do is the kind of embedding that we're generally familiar with. And so we're just going to embed each of these three things, well, technically two, because tails and heads are both nodes, right? We're going to embed both nodes and relationships just in the Euclidean space of dimension D. So if we say it's embedding 128, then each node, each relationship just gets a vector of length 128. And what we can do in Euclidean space, very, very simple, is we can say that we're going to add the relationship to the head in order to get a prediction point, and we're going to compare that to the tail. So it's very simple. So from this picture, which is just in 2 dimensions, you can say, you know, oh, this relationship R means you move to the right by, you know, quite a bit. Let's just call it 10, and then you move up 2. And so, you know, you add 10 to the x1, you add 2 to the x2, and then you get to this point, and then you compare how close are these. So what can we use as a scoring function? Well, we can just use regular L2 norm Euclidean distance, okay? Now, the only thing is we want smaller distances to score high. That means it's good, it's right, it's really close, and far distances to score low. So we are going to flip the sign on this. So if the head plus relationship is 10 units away from the tail, then we're going to give that a score of -10. If it's an exact perfect match, it's then 0. So the highest possible value for a scoring function is 0. All the other values are going to be negative. And then the more you get towards negative infinity, that means that you're really, really, really far away. All right. So that's the starting point. Does that make sense in terms of how we're using R is basically a translation vector that we're adding to it. So this is why it's called translation. Well, they don't spell, but TransE is short for like a direct translation embedding. All right. You guys go to that? Any questions about just this definition of TransE? All right. So moving on then. How are we going to train it? So in the Stanford lectures, they didn't really talk about this too much. I'm not going to go through the whole algorithm, but I did want to highlight something here. I checked out some of these different embeddings that we're going to look at, and they're all trained pretty much with this same methodology. And basically what you do is you take positive examples from your data where you have your head plus your relationship, and you're comparing it to your tail. But what they also do is they train it on negative examples. And so, as we've said, most of the time, these negative examples are created by corrupting the tail. So you take the head, you add the relationship vector, and then you pick an alternate destination node that does not exist in your training data. But the interesting thing about this is what you see here is, well, I don't know, they really go into the detail, but so most of the time the way these are trained, if you look at this gamma plus kind of a thing, what this little plus sign down here, it isn't really explained. What this little plus sign down here means is that we're going to take the max of 0 or this difference here, and what that means is that if your positive example and your negative, if your positive example it has a remember I have trouble saying all this because the scores are all negative numbers, and so like this is a side thing. But so if your positive example is close to 0 and your negative example is a really big negative number, really far away, 1,000 away, then 0 minus -1,000 is actually going to be +1,000. You're going to get a really big number here, okay? And in addition to that, we're going to add a hyperparameter gamma, a small number, like say like 1 or something like that. And so that is our loss function. And when we do gradient descent, right, we want to minimize our loss. And so so basically what is going to end up happening here is, because they're doing this max with 0 thing, is that anytime your positive example is at least gamma closer to 0 than your negative example, or more, then your loss is going to be 0. So what this is doing is it's not trying to perfect that your positive examples are exactly 0. Well, all it's trying to perfect is that the positive examples are at least gamma better than the negative examples. And if that's true for all training examples, then learning will stop because you'll have 0 gradient, okay? And so this is an interesting thing if you're familiar with support vector machines. This is basically introducing a margin. Gamma is the margin, okay? And it's saying that if all of your positive examples are at least gamma better than all of your negative examples, there is no gradient. The loss is 0. You've fully, you've gotten your loss all the way down to 0. The only time training happens is if your positive example isn't at least gamma better, or if it's actually worse. If it actually thinks the negative example is more true than the positive example, then of course you have a lot to learn. So you're going to have a very large gradient signal here. And so I just wanted to kind of point to that because I didn't do more digging to see in the literature why they use this instead of just a simpler, more direct loss. You know, if you look at like in computer vision, contrastive learning, SimCLR, or SimClear, some people pronounce it, it does not have this gamma business. It's just simply, you know, wanting to get positive examples close to 0 and negative examples, you know, to be really large negative. So I'm not really sure.
What that does is it prevents you from having a positive example. It forces you to positive examples that don't have a negative example near them. So like you said earlier, most of the negative examples will be really far away from the positive example, but that distance you're calculating there with D will be very large from most of them, but some of them will be close, and you want to make sure there's none of those that are close.
Yeah. Okay, good. So yeah, so maybe what's happening is that if you did this, you may find that you have lots of trivial negative examples that the model, it's very easy to say, no, you know, whatever, you know, Tiger is not the capital of the United States. Like, it's so obvious that it's just not the capital. But then he asks, you know, is Philadelphia the capital of the United States? And if it's not so sure, then you want your embeddings to push those apart. But it doesn't necessarily need to apply a gradient to learn something because it already knew that bear was, or whatever I said, tiger was just a ridiculous answer for what's the capital of the United States. And so it doesn't need to actually have any gradients for that. So that's what this thing is doing. It's saying, no learning if you're already very, very sure, but those really close ones that are wrong, we better fix it.
Okay, but if gamma is a constant, then its derivative is 0. What it is? It is not constant?
Yeah, gamma is a hyperparameter, I'm pretty sure, that you just specify up front.
Okay.
And then I'm not sure, I don't think gamma matters because your embedding space is arbitrary. You've just you know, made it up. But I do think gamma will interact with your learning rate. So if your learning rate's really small and your gamma is really big, then you're going to have something for vice versa. But otherwise, I think if you double your gamma and you double your learning rate, then basically your embeddings are identical. They're just twice as big, right? So instead of having an embedding of 101, you have a bit embedding of 202. So, all right. So anyway, so I thought that was kind of interesting that people have figured out that this is the way you do this margin learning. And again, I think that consistent with what Hobson was saying, some of the papers mentioned that you may want quite a few negative examples for every positive example. And I think it's because you need to try to find some plausible but wrong negative examples. And so one of the papers I saw that they said that 50 to 100 negative examples per positive example on the large data set that they trained on was kind of the sweet spot. And so you can see we're just 1-to-1, like, yeah, it might not learn anything if you just accidentally picked really dumb, obvious things like, you know, is the word tiger, you know, the capital of the United States? It's not even a city, it's not even whatever, it's just, you know, so obviously wrong. Yes, and that's a good point. In contrastive learning, you often need a lot of negative examples. SimCLR used some crazy batch size. I can't remember. I think it was something like 40,000 or something like that. And what it did was it compared each thing to all the others in that batch. And so that meant that it had this ratio of like 39,999 negative examples for every one positive example. And that was using ImageNet. Okay, so that's a little bit of detour talking about how we actually do the gradient descent for this model. But so if you have your training data, and we talk about this embedding where we have a d-dimensional vector for every node and for each relationship type. And now obviously all of our true edges and our corrupted bad edges, we just run gradient descent with a number of batches, and we do back propagation, and then eventually we will get embeddings that it's going to coalesce to embeddings. So this is basically, right, like I was saying, this is like word defect, where eventually it converges to a set of embeddings. So now what we're going to talk about are the different kinds of patterns between different relationships and how that may or may not cause you problems if you're trying to learn this kind of embedding. Okay, so some examples here, we're actually going to get into it, but like the roommate type of relationship has this symmetry where if H is a roommate with T, then T is also a roommate with H. Okay, you may have two relationships that you want to be inverses of each other, that if H is an advisor for T, you want it to be true that T is an advisee for H. All right, so what are some of the different categories? And we're going to talk about like 4 or 5 just different categories for patterns between relationship types. All right, and so these are symmetric, inverse, compositional, and one-to-n. So symmetric, again, is like roommate. If A is a roommate of B, B should also be a roommate of A. Inverse relationship, we said, was advisor advisee. There's one that's not on here. Oh, I see. It says as anti-symmetric was on the same bullet. So you can have symmetric relationships like roommate, but you can also have anti-symmetric relationships. So they have, as example here, hypernym. I didn't remember what that was. I had to look it up. But so like hypernym sort of like is a kind of. And so you would expect that if you have a relationship red is a kind of color is true, then color is a kind of red should always be false. That if one direction is true, the other should always be false. I see in the chat question about negative examples. Generally speaking, in all machine learning, when you need negative examples, it's hard to have provable negative examples. And so you're just doing a probabilistic thing. We would love to have perfect examples. But so like SimCLR, when it does its images, it's got that ginormous batch of thousands. I believe it was in the tens of thousands. And it's just saying that the different image augmentations of a particular image are known positive examples. And it treats all 39,000 of the other ones as negative examples. But the reality is there's only 1,000 classes in ImageNet. And so if image 1 is a dog, there will just by chance be a few other dogs in that batch. And so you're actually giving it the wrong signal. But since there's 1,000 classes, the probabilistically speaking, they're going to get outnumbered 999 to 1. And so on average, your gradient learning signal from the net example should be pretty good because you're not going to get that many dogs. But they did find that that was enough to cause real problems with learning. And that's why they needed the batch size to be that big. SimCLR did not work if they just used a normal-ish large batch size of 16,000. Of 1,600 or 2,000 or something like that. They really needed ginormous batches to make sure that those false negatives got drowned out. Okay, so just going through the 5 relations. So compositional is an interesting one. So it's like, yeah, so here. So if you have a relationship called mother and a relationship called husband, then if A to B is B's the mother, and if B to C, C is the husband, then you know that A to C is a father relationship, okay? And maybe this is not a perfect thing or whatever, but let's not get hung up on that. You get the gist of this, Okay, so can you do this sort of transitive logic? And then finally, you also don't necessarily have one-to-one relationships. You could have one-to-n relationships. And so imagine you have student of. And so it's going to be a problem if you can only have one person who's a student of, if it doesn't allow for the possibility for multiple people. So let's take a look at this thing we just talked about, TransE. Okay, and let's see how well it does with these 5 different things. So anti-symmetric relationships, not a problem. So if you say red is a color, and then you ask, is color a red? Well, if this hypernym relationship is this R here, then red goes to color, and then when you say color to whatever, it's all the way over here, not back at where you started. So check mark, this one does pretty well. Inverse relationships, yeah, absolutely. If you do -1 times a relationship, and you learn that that's what the vector for relationship 2 should be, then they will perfectly mirror each other in this TransE embedding model. What about composition? Well, that actually works very well because we're doing Euclidean translation, and so this is just the triangle property. So if you add R1 and R2, then you can just set R3 to be the sum of those 2 vectors, and in fact, if it's mother, husband, and father, then boom, these things will work well. But TransE doesn't do some of the other ones. So symmetric relationships. If you're looking at roommate, if H is roommates with T, T can't be roommates with H because the vector R is going to go all the way out here. Obviously, there's a pathological case where you set the relationship to be the 0 vector, but you can't have all symmetric relationships have 0 vectors. And not only that, if you do that, then that means that the embeddings for every pair of roommates have to be identical, and that's not going to work for all your other relationships and things like that. So so symmetric relationships do not work in this simple TransE model. One-to-many relationships also don't work because basically you can have a valid relationship student of, but then basically it wants every other student of to be in the exact same place. Okay. So so it did well on 3 of them, but not on these other 2. All right, so I'm going to pause here. I know that for some of this stuff, I'm going relatively quickly. There is a fair amount of material in these lectures, so I insert these just to make sure that I breathe and give you guys a chance to ask questions or catch up if there's anything. So you guys good with TransE? All right. So
really
for the
helpful.
thing, sorry?
Oh, this is really helpful. Thanks.
Okay. So the relationship types that we showed that worked, so like anti-symmetric relationships and transitive ones, if that's what you have in your knowledge graph, if you only have those 2 kinds of relationships, then TransE will probably work quite well if you then train your data in this fashion. But what if you have some of those other ones that don't work? Then what do? Well, we're going to talk about 3 other ways that you can do things and possibly get better embeddings. So TransR is an extension of TransE, and there's other ones. There's a TransH and whatever. So in TransR, what we say is instead of just having a simple Euclidean space, I said before, I think 50, right? So that you do all relationships. What you can do is you can do every different relationship in a separate space. There's a number of ways you could implement this theoretically, but what we're going to do is we're not going to have separate embeddings for every relationship. That's not going to work. Okay, that will overfit. So instead, what we're going to do is we're going to have a single mapping matrix that will map from our default embedding space into a relationship specific space. So for every relationship type now, in addition to having a relationship vector, we also are going to have a relationship matrix that maps our embeddings into a different unique space just for that relationship. So here's the idea. Maybe the pictures were a lot better than me trying to use words. So here's our embedding. Again, this is just showing two-dimensional. We have our T and our H, but what we're going to do is we're going to multiply these vectors by this relationship matrix M. And that's going to give us, if you guys know your linear algebra, right, that's going to convert us to a new space. And in this case, now we're going to measure our relationship R in this space. So everything that worked in TransE will still work because we could always just have M be the identity matrix. But the question is now, are there a couple new things that we might be able to get to work using this? So how about those symmetric relationships, the whole roommate thing? Okay. Theoretically, we're not saying that this will work when you train your model, but theoretically, this can work because even though you have two different roommates that have different embeddings, the mapping matrix M could map them to the exact same point. And so this solves that problem that we had with TransE, where you can have a relationship from one to the other, but then the reverse won't necessarily work. But if you map these on top of each other and have the relationship vector be 0, then you're golden. So at least in theory, it has the capability of mapping. Yes, there are multiple M's, one for each relationship type. And so generally speaking, the things that didn't work in TransE are the ones that you really need this mapping. Theoretically, the other ones, it'll still do it, but hypothetically, identity matrix would still work because they already work. All right. And so we have the anti-symmetric relationships. Those always work just fine. Right. So two people, just because the roommates aren't the same person in your embeddings, but they are the same person in your mapped space for that particular roommate relationship. And what about one-to-many? So again, the same thing that that we did for symmetric. You can just map multiple students to the same point, and therefore they'll all be student of the same professor. Inverse relations, again, of course they work because they work for TransE. And this is an interesting thing. Composition gets tougher. So this was the one where you say, my mother's husband is my father. Okay, this did work in TransE, but now there's the possibility that the mother space and the husband space and the father space are different, and they don't there's the possibility that they don't work, but I think I'm not sure if I understood the all the math on here, but basically I guess bottom line, the way it works out is yes, one of two things are possible. Either it works, or also that you can just learn embeddings for relationships that have to work like this, that are compatible or identical or whatever. So it is possible that since these are linear functions, that they are chainable and that everything will work out just fine. All right, there's this slide. I'm not gonna talk to this slide. It goes into a little bit more here, but that's for, again, these composition things, these transitive things like my mother's husband is my father. All right, so the main thing is we took TransE, and now instead of just looking at the embeddings raw, we translate them all in a relationship specific way, and that gives us more flexibility than we had with just TransE. All right, any questions? Okay, so TransR was pretty similar to TransE. We're now going to get something different. We're going to get this dist-molt model, and we've been using like a L2 Euclidean kind of a distance. What we're going to now use is basically like a cosine similarity. We're going to use a dot product. And so the idea is that if you have a vector for your head, a vector for your relationship, a vector for your tail, then what we're going to do is we're going to dot all three of them together. So we're, right, you component wise multiply all of them and you sum it up. And that's what we're going to use as our score function. So I don't know if this intuition helps some of you, but basically, if you look at head.r, basically, that is going to define a particular vector. So this black vector here is head.r. And then in 2 dimensions, what's perpendicular to that is a line. In 3 dimensions, what's perpendicular to a plane, and in higher dimensions, it's a hyperplane. But that basically, all of the points that are on that hyperplane are going to be orthogonal to it. They're going to have, a 0 dot product. Everything that's below that hyperplane is going to have a negative number, and then everything above it's going to have a positive number. And so you can kind of think of the relationship function as defining this hyperplane by which we're measuring the tail vectors against. If that intuition helps, great. If not, I don't think it's necessary. The main thing is just think of it as a dot product amongst the 3 of them. Okay, so the one of the things that we want to be able to do in dist-mult that we couldn't do in TransE is these one-to-many relationships. And again, the idea here is that for any given value of this dot product, there's always going to be sort of this circle, this infinite number of different points that all have the same distance. And so you could have n students that all have the same distance, the same score when it comes to the relationship between the head and the tail. And so that's how this can solve for one-to-many. Symmetric relationships, totally fine, because the dot product is inherently symmetric. So you're going to get the same answer if you do head relation tail as if you do tail relation head. But anti-symmetric, we're going to have a problem. Okay, the same thing we said for symmetric. Head relation tail dot product is always equal to, so basically every relationship is going to be considered symmetric. And so we have a problem if we don't want it to be symmetric. Inverse relationships, it's sort of a similar problem. So advisor, advisee, you kind of run into a problem because again, the dot products are symmetric. And then finally, this one, the composition, the transitive one. So again, my mother's husband is my father. Doesn't naturally extend. Again, the idea is if you think of a relationship as defining a hyperplane that cuts the positive and the negative examples, you can't really composite hyperplanes. And so you're going to have a problem with this one. You're not going to be able to do composition. All right, so this one was a little bit different, a little bit more gnarly. Not sure if I covered it completely well, but the main idea is that now instead of using Euclidean distance as our scoring function, we're using this dot product as our scoring function. Any questions?
Not exactly question, just some observation. And I'm saying it with love as mathematician. It looks like stuff which mathematicians pull out of the thin air without any care if somebody can produce them. So I'm very interested in practical implementation.
Yeah, and if you look, so each of these has a link to the paper. So the papers, they do actually have where they trained it on these public data sets, and they showed that like they were able to get embeddings that work better for certain things than others or whatever. But it's a very valid point, right? Yeah, right now we're just talking about theoretical spaces in which we could put our embeddings, but you know, at least know that these things really did work when they when they implemented them.
Okay.
I think I don't remember I don't know how old TransE is, but I think these other ones were like 2015 and more recent, so they're fairly new. And so people did have like GPUs and stuff to run them on, and they did actually test them out. All right, so the last one is called complex, and this is a relatively small tweak to the last one that we saw. All we're doing is we're taking distmult, and instead of using real valued embeddings, we're using complex numbers, okay? And the slight tweak that we make is that we were doing the dot, so if everybody knows what a complex conjugate is, so if you have a vector u that has a real component a and a complex component b, then we say that u equals a plus bi. If we flip the sign on the imaginary part, that's the complex conjugate. So u minus the u conjugate equals a minus bi, and b can be positive or negative, but you're just always flipping the sign in order to get the conjugate. So the tweak that we're going to make is we're not just going to represent our vector as d sets of complex numbers instead of d sets of reals. Our dot product here, instead of head.r.tail, we're going to do head.r.conjugate of tail. And this little tweak is what's going to give us a little bit of flexibility to handle those symmetric anti-symmetric relationships. Okay, otherwise everything's the same. So for the anti-symmetric relationships, okay, so like red is a color, but color is not a red. What you'll see is that, let's see here. What's the vision for this? So, so basically, the dot product of head r tail conjugate is not the same number as tail r head conjugate. So whereas before these were always the exact same value, these do not need to be the same value. Okay, and so so that's how we break sort of that symmetry between head and tail. Okay, so I think in particular, if you imagine the real and the imaginary components, like the real component is big and the imaginary component is small, then when you do this, then the imaginaries that multiply together to get a -1, you get a small thing, whereas the other way around, you get a big thing. Okay, now symmetric relationships. Oh, sorry. Going back to here, we take the dot product of these three things: the head, the relationship, and the complex conjugate of the tail. Then we take only the real part of it. We drop the imaginary part of it. Okay, so even if you have a large imaginary component, we're just dropping it completely. Okay, we're projecting down to real. So symmetric relationships, you can show, easily models that. That's not really difficult at all. Inverse relationships, not a problem, because if you set relationship 1 equal to the conjugate of relationship 2, then it's true that the dot product of head r tail conjugate is the exact same value as the dot product of tail r head conjugate. So before we said that wasn't necessarily true for any relationship, but in this case, relationship 1 and relationship 2, we purposefully set to be conjugates of each other. in terms of composition and one-to-one relationships, complex shares the same properties as dist-mult. So basically, we just have added this little twist to help us with some of the trouble that we had, where the dot product was always symmetric. Now things are not always symmetric. All right, so thankfully, there's a table that that summarizes the different yeses and nos for these 4 different embeddings. So I'll show that in a second, but just before, because I think that will help. But before that, any questions on just this little tweak to dist-mult where we're now using complex numbers instead of real numbers? All right, so phew, luckily this table summarizes things. TransE, again, we're using the Euclidean norm, again, minus sign, just because we want 0 to be a good value and a large number to be a very negative value. So the 3 things it does well, the 2 things it doesn't. TransR helps with that. Dist-mult it has a different, it's now not using Euclidean, it's using this dot product form. And it has some significant limitations, but by switching to complex numbers and taking the real component of this dot product, then you solve for most of that. And so what Professor Leskovich says in the lecture is that no one of these embeddings is clearly always better for all knowledge graphs, depending on the types of relationships that you have. So a simple kind of rule of advice is start with TransE. It's simple, it's intuitive. If things don't work, there's clear intuition on why they don't work. And so this is fast, and so you should start with that. And if that doesn't work, then you can start doing other things, like you can use complex, and you can also use a complex version of TransE, which is called rotate. And so you can try other embeddings. And again, if you look at the different papers, you can see where they have actually run these on large knowledge graphs and gotten whatever up to 80% accuracy on this knowledge graph completion task. Okay, so to summarize, basically link prediction graph completion is an important task, and so we have these different embeddings, and no one is like the king. So just like with a lot of other things in machine learning, you may actually try multiple models, and the idea of parsimony probably applies. If you get similar results with TransE and complex, you're probably going to just go with TransE.